Hey everyone, welcome to assignment 47. We're going to be pulling things together in this video. We're going to be reviewing some stuff. We're going to be putting things together from our last few videos. Let's start with end behavior. What's the end behavior for y equals negative 2x to the third plus 5x plus 7? Okay, think about that. Pause the video if you need to. Remember to write your answer using our end behavior notation. That's really important, which is not what it says in the back of the book. I don't want to hear anything about rising and falling. I want to see some good notation when we take this assessment. Okay, so negative x to the third looks like this. And so I say as x heads to negative infinity, as the x's go this way, the function seems to be going up. F of x heads to positive infinity. And as x heads to positive infinity, as we go this way, where's f of x headed? Well, it looks like f of x is headed down. F of x is headed to negative infinity. Okay. So what about this f of x? Y equals, or f of x equals 5x to the fourth minus 3x to the third plus 4x. Are you all remembering to think about zero placeholders? We don't need them to answer the question, what's the end behavior for this fourth degree polynomial with a positive leading coefficient? But we're not done with zero placeholders, so do keep thinking about them, just like, ooh, we would have needed one there too. All right, so pause the video, think about this for a minute. I want to know the end behavior with good end behavior notation. Welcome back. So as x heads to infinity, as we go this way with this positive even degree polynomial, I know my even degree polynomial looks like this on the ends. So I say f of x heads to infinity, and as x heads towards negative infinity, as I go this way, I know that f of x is still headed to positive infinity. If there had been a negative in front of this 5, both of these would point down, so both of these would be negative. Okay? So we have to be thinking about end behavior right at the beginning of breaking down our polynomials. But if our polynomial is already given to us in a broken down form, like this, we should be pretty comfortable making a graph from factored form. Think about x-intercepts, think about end behavior, think about bounce, wiggle, and pass through, and think about the y-intercept. So pause this video, give this one a try, come back when you're done. That's right, this one has x-intercepts at negative 1, 2, and 5. Negative 1, 2, and 5. Great. Now, what degree? 2 plus 1 is 3 plus 2 is 5. This is a fifth degree polynomial. X squared, that'll be positive, times a positive x is a positive x to the third, times a positive x squared is going to be positive x to the fifth. So positive x to the fifth has this kind of end behavior. So I know I'm just going to pass through. Don't forget, bounce, bounce. I'm going to pass through and go that way. My y-intercept. Remember, I find a y-intercept by plugging a 0 in for all the x's. I put a 0 here. I don't just get negative 2, I get negative 2 squared, which is 4. If I put a 0 here, I get 1. If I put a 0 here, negative 5 squared is going to be positive 25 times 1 times 4 is 100. Okay? So, yes, we can do that. Let's do one more. You should be comfortable with this. Y equals 4 minus x plus 2 to the third, x minus 1 squared. Okay, pause the video, graph this up, come back when you're done. Okay, so did you notice that the x-intercepts are at negative 2, positive 1, and positive 4? Negative 2, positive 1, positive 4. And what's the degree of the polynomial? Well, 1 plus 3 is 4, plus 2 is 6. Sixth degree polynomial. Does this have a positive or negative leading coefficient? Well, here I have x squared, that's positive. I have positive x to the third. When I multiply those, I'm going to have positive x to the fifth times negative x to the sixth. Okay, so I know that both ends go down for this even degree polynomial with a negative leading coefficient. I know at 1 I'm supposed to bounce, I know at 4 I'm supposed to pass through, and I know at negative 2 I'm supposed to wiggle. Okay, so I know many of you are still not comfortable with the wiggle. So here's what I want you to think. I want you to think of one of these two ways of doing it. You are comfortable with this. Oh, I'm sorry, you're not comfortable with the wiggle, but you are comfortable passing straight through. So I'm going to pass straight through at 4. I have to bounce at 1. And then I have to think about connecting this with this. And remember, a wiggle looks like either x to the third or negative x to the third. Here's negative x to the third. Well, can I make this connect to this and this connect to this in such a way that this stays a function? Well, let's see. Oh, fails the vertical line test. That's not going to work. I can't connect those. So it's not going to be this wiggle through at x equals negative 2. It's going to look like positive x to the third. So there's my going down forever, and there's my connecting up. So it may be useful for you to do two things. One, start on the side of the graph that you're more comfortable with, because that can inform you over here a little better. Also, remember that there's only two choices. I'm going to look like this one, or I'm going to look like that one. And I've somehow got to connect from where I am to where I expect to be. And that's awkward because that's going up forever, and I need to be going down forever because this is a negative leading coefficient. All right. So, you know, we've seen all that stuff before, and now we come to this. Y equals x to the fourth minus x to the third minus 30x squared. And again, you know, I'm not really troubled by this because we've gone through the algebra basics unit, and I know if I'm trying to get this polynomial in factored form, the first thing I do is GCF factor. And I notice I can take an x squared out of each of those. So I get x squared minus x minus 30. And I hope that we're all comfortable factoring that polynomial, that trinomial, that quadratic trinomial into x minus 6 and x plus 5. It may be helpful for some of you to rewrite this as x minus 0 squared, if for no other reason than to remind you that there's an x-intercept at 0, and the graph is going to bounce there. Okay? That's what this is telling me. This is telling me I've got an x-intercept at 0 and a bounce. So my graph, no problem, negative 5, 0, 6, positive x to the fourth, so both ends are up. And I know at 0 I'm supposed to bounce and down. And there's my graph. Okay? So factoring is this really powerful thing. Why don't you show me the graph of this one? Y equals x to the third plus x squared minus 4x minus 4. Pause the video, get this in factored form, and then graph. Welcome back. So I can group these in pairs. Remember to capture that negative inside these parentheses. X plus 1, minus 4, x plus 1. We've got two terms here. Both of them have a common factor of x plus 1, which we can take out. What's left over? An x squared and a minus 4. A difference of squares. And so that's going to be x minus 2, x plus 2. Everybody has a multiplicity of 1. And so I've got negative 2, negative 1, positive 2, third degree polynomial with a positive leading coefficient. We're going to look like this. And my y-intercept is -4 because when I plug zeros in for the x's, that's all that's left. Don't forget to label your y-intercept on your polynomial graphs. Many people forget this, and then it gets marked wrong, and they're all sad. So please make sure you label that. Okay, so factoring, all that factoring that we did in the Algebra Basics unit was in part to get us to be able to do this breaking down of polynomials so we could graph them more comfortably. How about this one? Y equals x to the fifth minus 6x to the third plus 9x. Give this one a try. Okay, I understand that some of you found this troubling. Remember, we're trying to factor this, and I see a common factor of x. And then we had talked about using parallel structure, right? I need to factor this, and it's the same setup as this. If this factors as x minus 3, x minus 3, because this middle term is x to the first, then how is this going to factor? Well, this one's going to factor as x squared minus 3 times x squared minus 3 because the middle term is an x squared, okay? Don't forget, this isn't the complete factorization. If I FOILed this, I'd only get back to x to the fourth. We started with x to the fifth. Remember, we factored out that x. And yet, I see difference of squares here. I see x minus root 3, x plus root 3. These FOIL to make that. And here again, x minus root 3, x plus root 3. And don't forget that x out in front. And that's right. Look, we got 2 of those, and we got 2 of those. So really what I could do here is write, I guess I'll change color so we have a chance of seeing it, x times x minus root 3 squared, because we've got 2 of them, and x plus root 3 squared, because we have 2 of those. And so look, at x equals root 3, we're going to bounce. And at x equals negative root 3, we're going to bounce. So, what do we have? We have 0, we have root 3, we have negative root 3. We have a fifth degree polynomial with a positive leading coefficient. So I'm bouncing, passing through, and bouncing. Kind of cool graph. Nice. And that wasn't so hard. We had to do a little factoring. We had to remember about bounces and wiggles. But yeah, once we get comfortable with that stuff, this goes pretty nicely. Why don't you try this one? I bet you'll be very confident with this. X to the third minus 25x. Okay? I'd like to see a graph of that, labeling x and y intercepts. Use your factoring skills. Pause the video and give it a try. Okay, I like to think you all started by factoring out that x, and then you all saw that difference of squares there. If you didn't see the difference of squares there, I think you should really probably go back to that Algebra Basics unit and spend a little more time in the factoring section getting comfortable with this stuff, because it's not going away. I promise. I see x-intercepts, 3 of them. This one is at x equals 0, this is x equals 5, and this is x equals negative 5. Negative 5, 0, 5, positive leading coefficient. And I'm just going to pass through at all of those because I don't see any multiplicity of 2 or 3. All right? So that's where we've been, but now what about where we need to be next? Well, that's very interesting. I have a little note here that says while we're talking about this stuff, we should maybe go back even to the beginning of the unit and remind ourselves, how do we graph this? Remember at the beginning of the unit, we talked about not rewriting these quadratics, not rewriting these parabolas, but just graphing them from whatever form we're given. So here's our general form, and I remember graphing from general form. I want to find the vertex, and I can find the x value of the vertex by doing minus b over 2a. So that will be minus 3 over 2 times 1 half. Okay, those cancel. I get minus 3. So minus 3 is the x-coordinate of the vertex, and I need the y-coordinate of the vertex as well. I think I'm going to use synthetic substitution for that. Negative 3, 1 half, 3, 5. Bring down the 1 half, I multiply, get negative 3 halves. So this is 6 halves minus 3 halves is 3 halves. I multiply, it's negative 9 halves. That's minus 4 and a half. 5 minus 4 and a half is 1 half. So remember from the remainder theorem, when we divide by this number and we get this remainder is the y value at that point. So we know that the vertex is going to be located at negative 3, 1 half. Okay? So we've got our vertex, we see the y-intercept, and remember we'll do a third point with symmetry. Because this is a positive 1 half x squared, we know that our graph points up. Here, negative 3, 1 half, y-intercept of, 0, 5. And then over here, remember with symmetry, if this distance is minus 3, there's another minus 3, so minus 3, this will be negative 6 with the same y value as the y-intercept. Okay? So there's our graph. We did have to remember that. Yes, you do need to remember that. Yes, it is on our unit test. And then what about y equals negative 2x plus 1 squared plus 5? You could certainly use transformation graphing here. You could also remember that this was vertex or standard form. Remember vertex or standard form with x minus h squared plus k, where the vertex is located at hk. So I see our vertex here inside his opposite land is negative 1, and there's our y value, positive 5. We have the vertex. To find the y-intercept, I have to plug in a 0 for x. 0 plus 1 is 1. 1 squared is 1. 1 times negative 2 is negative 2. Negative 2 plus 5 is 3. So I know the y-intercept is at 3. This is a down-pointing parabola. And so we've got 0, 3. We've got negative 1, 5. And if I use symmetry, this was minus 1. This will be minus another 1. So this will be minus 2, positive 3. And there's my graph. Okay? And finally, we needed to be able to do this from our intercept form. Minus 3, x plus 1, x minus 5. Oh, hey, this is probably a good time for me to say to you, no, we're not done with graphing when we get to the polynomials unit test. In fact, one whole day of our semester exam, which does go on for a number of days, one whole day is graphing. So we definitely need to be comfortable with it. In intercept form, I see that the x-intercepts are negative 1 and positive 5 because inside is opposite land. This does not make any x-intercepts, right? I'm setting x plus 1 equal to 0 to find x equals negative 1. I'm setting x minus 5 equal to 0 to find x equals 5. Okay, negative 3 equal to 0. No, it doesn't. This is a vertical stretching factor. It's not a factor for the purpose of finding x-intercepts. It does tell me my polynomial is pointing down and was stretched vertically by a factor of 3, but all I need is to graph these. I know that the vertex is halfway in between those points, but really, I just need 3 points on the graph, and the y-intercept could be the third one instead of the vertex. If I wanted the y-intercept, I would plug zeros in for these x's, and I get positive 15. And that's pretty fast. I can find this vertex. I probably wouldn't do it by foiling this out and using minus b over 2a. I myself would probably add these numbers together, negative 1 plus 5, and average them. The average of the x-intercepts is the x-coordinate of the vertex. So if I plug a 2 into each of these, I'm going to have 3 times negative 3, which is negative 9, times negative 3 is positive 27. So 227 there. Okay. So please make sure that you can graph not just these higher order polynomials that we've been talking about more recently, but also that you can feel comfortable with quadratics, because we certainly talked about those. All right. Well, we then, hold on, there's a little more review to get through. Can you write me the equation of this polynomial? This is 1, 6, and this, oh, that is definitely not drawn to a scale that you're going to be happy with, is 0, 3. Okay? So please write me the equation for this polynomial. You don't remember? Well, we're going to use vertex form because we know the vertex. And we wrote down this general form where h and k is the vertex. So I know that this is a x minus 1 squared plus 6. Now what about that a? Well, that's why I've been given this other point. So I can plug a 3 in for y and a 0 in for x. And I get 3 equals a plus 6. A equals negative 3. So I'm not done yet. I have to take this and plug it in here. So what will that look like? It will look like negative 3 x minus 1 squared plus 6. And there's our equation. All right? What about this one? Can you go and tell me the equation for this one? We've got negative 1, positive 5, and 0, negative 10. Okay? So please write the equation for this quadratic. Welcome back. I hope you used intercept form because you have the x-intercepts. Y equals a, x minus b, x minus c. And so we've got y equals a, x minus a minus 1, x minus 5. Yes, I'm going to tidy that up to x plus 1, but I wanted to show you that we're always starting with a minus, and when I plug a minus into that, with that minus, I'm going to end up with a plus. Some students say they just always use the opposite value. Here's a positive 5, there's a negative 5, here's a negative 1, there's a positive 1. But we still have to find a, and yes, that's why we have this. Negative 10 equals a, 0 plus 1, 0 minus 5. And so I get negative 5a equals negative 10. And so a equals positive 2. So let's take that a value and plug it back in. And there we are. All right. Okay. So what about this? Can you write me this equation? I have intercepts at negative 2, at 0, and at 3. And my graph does this. Oops. My graph does this. Like this. So can you write me a possible equation for this polynomial? I hope so. I like that idea of rewriting the x-intercepts as factors. And, ooh, that's a bounce. And that's a wiggle. And 2 plus 1 is 3, plus 3 is 6. Good, this is a 6-degree polynomial, but look, they both go down. I need to put a negative in front. You know, if you wanted to put a negative 4, you could certainly put a negative 4 there, even a negative 10 million. But we definitely need to have the negative. That's the important part of that because our graph has end behavior with both sides going down. Okay? Can you write this one? Let's bounce at 3. There's 1. Here's 0, negative 54. And this point is negative 2. Okay. Please write the equation for this polynomial. And unlike the last one, where you could have lots of different coefficients, because of this given extra point, no, we're only going to have one. You're looking for the polynomial. Okay. So, nice. Did you come up with x plus 2, x minus 1, x minus 3 cubed? Well, what about an a value? Should we be worried about that? Well, you know what? Negative 3 to the third is negative 27. Negative 27 times negative 1 is positive 27. Positive 27 times 2 is 54. But I see negative 54. So what has to happen here? Well, let's plug in the point and see. Okay, 0 plus 2, 0 minus 1, 0 minus 3 cubed. Okay, so I'm going to have negative 27 times negative 1 is positive 27 times positive 2 is 54a equals negative 54. When I divide both sides by 54, a will be negative 1. So there is an a value. I can't assume, and I want a negative 1. Now, this seems surprising to me because these ends are going up. So why would I have a negative leading coefficient? Any thoughts about that? I kind of want to look at this again. Oh, there it is. Do you see it? That's a bounce. It's not a wiggle. 2. So that's going to change this a little bit. 2. Now I've got positive 9 times negative 1 is negative 9 times positive 2 is negative 18. So negative 18a equals negative 54. So a equals positive 3. And now I feel better. See, it's really important that we do some thinking. You're not, you know, the algebra monkey is able to process information, but the hominid, you, the evolved form, the hominid is able to say, wait a minute, my a value shouldn't be negative. I'm going both sides up. And that should encourage you to go look for a mistake. Okay? All right. So, almost done with the review part. But no, really, I've learned that if I don't do this review part now, things go badly. So, hey, remember the box problem? Not going away. Not going away. You need to know how to do this problem. Okay? Let's say that this is 20 centimeters and this is 16 centimeters this way. And we're going to cut little x by x squares out of each corner. And we're going to then fold this up to make an open-topped box. And so, can you write the formula for the volume of this box? And then, of course, I'm going to ask for the domain, and then maybe we should talk about finding the maximum volume your box can hold. Okay, so this is this. This whole piece is 20. This is x. This is x. I want this. So I'm going to take this whole thing and take these two x's away. And then this is this. So this is 16 minus 1x minus 1x, or 16 minus 2x. And then finally, this is x, this is x. This height is x. When we fold up this flap, we lift it up. When we fold up this flap, they meet to make that height of x. So v of x equals x, 20 minus 2x, 16 minus 2x. Now I already know I can graph this pretty quickly. 0, 8, 10. This gives me 10, this gives me 8, and there's, of course, x minus 0. So I see some negatives here. Is this a negative leading coefficient? Am I coming this way? Well, negative 2x times negative 2x is positive 4x squared, times x is positive 4x to the third. So no, I'm just going to write this. Okay, so these are x values. These are volumes here. The next thing we're asked to do is to consider what's the domain of this function. Now, for a polynomial, we know the domain is all real numbers. But in this application problem, does it make sense that volume can be negative? Do you want a present with a negative volume? No. So all these have to be thrown away because those are volume less than 0. And all these have to be thrown away. But what about over here? Here I have positive volume. What if I have 20? Is there any issue with 20? Well, remember what x represents. These are x values. X represents how much we're cutting out from each side. Okay, I want to cut 20 off of this side and 20 off of this side. But the whole thing is only 16 long. How could you possibly take 20 off of each side if the whole thing is only 16? You can't. And so this doesn't exist either, even though we have positive volumes over there. So what am I left with? Well, just 0 to 8. Domain is 0 to 8. Why am I using parentheses instead of brackets? Well, brackets would imply that I was happy with a volume of 0. Let me ask you this question. If Mom was going to give you a present and she put it in the box and she told you, by the way, the box has a volume of 0, are you happy child or sad child? Most are sad child because they don't want a present from a box with a volume of 0. That means there's nothing to it. There's nothing inside of it. No space for you. Oh, by the way, this I want to remind you about this maximum volume thing. We had this, and this was located at 8. Many students want to say that the maximum volume happens at 4, and that's almost always wrong. The only way we're going to be able to find this maximum volume is using our graphing calculator and doing second calculate maximum. At least until we get to calculus. When we get to calculus, I'll show you a nifty, easy way to find where that maximum is and what the value of that maximum is without needing to use your calculator. All right, so we're almost done with the review. Here's a g of x. X to the third plus 3x squared minus 6x minus 8. All right, find g of 1. And of course, I want to know what g of 1 means graphically in this situation. Okay, so 1, 1, 3, negative 6, negative 8, 1, 1, 4, 4, negative 2, 2, negative 10. G of 1 equals negative 10. So there exists on the graph of g of x this ordered pair. This is the y value at that x value. There is an ordered pair on the graph. I also know that that's not an x-intercept because what should I get as a remainder if this is going to be an x-intercept? The factor theorem says my remainder needs to be 0. Okay, so how about g of 2? Will you find g of 2 for me? Did you get it? Did you say 2, 1, 3, negative 6, negative 8, over 1, 2, 5, 10, 4, 8, 0? Now what can you tell me about g of 2? Well, we know g of 2 is equal to 0, so That's right. X equals 2 is an x-intercept. Okay? So now that we know one of the x-intercepts, we could do some division and break this polynomial, this third-degree polynomial, down to a second-degree polynomial. Well, wait a minute. We can take this further. We know that this is 1x squared plus 5x plus 4, and that's going to factor as x plus 4, x plus 1. Don't forget the original x minus 2. There's our factored form. And lo and behold, we can now graph negative 4, negative 1, positive 2. And this is third degree polynomial with positive leading coefficient. Oops. And remember what we said about g of 1. G of 1 was negative 10. And so there's our nifty graph. Ooh, look. The y-intercept is negative 8. But negative 10 has to be below negative 8. Ooh, let's change the graph to reflect that. There we go. So that's positive 2, negative 1, negative 10. I'm sorry, positive 1, negative 10, and 0, negative 8. Okay, nice. So we've got this review of factor theorem and remainder theorem. We can use synthetic division to break up a polynomial. And of course, that leads us to these. So 2x to the third plus x squared minus 6x minus 3. And I know that square root of 3 is an x-intercept. Okay, so root 3, 2, 1, negative 6, negative 3. 2, I multiply. 2 root 3, I add. No, it's not 3 root 3. This doesn't have a radical. It has to be 1 plus 2 root 3. Now I'm going to multiply this to each of these. That's distributing. Root 3, 1 plus 2 root 3. I have to distribute. And so I'm going to end up with root 3, and then 2 root 3 times root 3. Well, root 3 times root 3 is 3, times that 2 is 6. And I add these, and conveniently this minus 6 and plus 6 cancel out. And then root 3 times root 3 is positive 3. I add these and get 0. So it's true, root 3 is one of my x-intercepts. Now, think about this polynomial for a moment, right? This was third degree, so this must be second degree. And you know what I don't want to try and factor? This, which is why it's terribly, 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 terribly important to remember that irrational roots always travel in conjugate pairs. So if we have positive root 3, we're also going to have negative root 3. Notice I'm not doing negative root 3 into the original polynomial. I'm doing this negative root 3 into this second degree polynomial because I'm trying to bring the degree down even further. So bring down that 2. Negative root 3 times 2 is negative 2 root 3. I add, I get 1. I multiply these, negative root 3. Yep, that is an x-intercept because I got a remainder of 0. Now, here, this is kind of very important. Look what we've got here. Okay, so we started off with 2x to the third, it went down to 2x squared, and now this is 2x plus 1. Okay, so let's think about this. We've got x minus root 3, we've got x plus root 3, and we have 2x plus 1. And what I like about this is that I've got x times x is x squared times 2x is 2x to the third. That's fabulous. And I know if I took the time to FOIL it out like we did in our Algebra Basics unit, we'd be able to get back to this original polynomial. But I want to come back and I want to look at this a different way. What if we had been told that this was a factor instead of this root 3? So we had 2x plus 1, and we set that equal to 0, and we got x equals negative 1/2 to do our synthetic division with. Okay, so let's do our synthetic division with negative 1/2 2, 1, -6, -3. We already know this is a factor, so we know we're going to end up with 0. If we don't, we've got a mistake somewhere. We'll bring down that 2. 2 times -1/2 is -1. Oh, that's 0. Nice. And then here, oh, that's 0. -6. -6 times -1/2 is +3. And then, sure enough, there I am. But check it out. This is a third-degree polynomial, so this must be a second-degree polynomial. So I'm looking at 2x squared minus 6. Okay, so 2x squared minus 6. 2x squared minus 6. And I want to factor that down. I want to break it down further. So pull out a 2, x squared minus 3. And now there's a difference of squares. X minus root 3, x plus root 3. And you know, if you're not comfortable seeing that root 3, you could always set this factor equal to 0 and solve. Okay, so that's where I'm getting that plus and minus root 3 from. And then GCF factored out that. Is this that polynomial? Well, no, it can't be, because x times x is x squared, and I have x to the third. Don't forget this. And here's the issue. Students now do that. And this is not this. What? Check it out. Oh, wait. Is this? Oh, I take that back. This is that. Because look, when I distribute this 2 to each of these, phew, I get that. All right. Okay. That works. There is something with this. There is something with this form. It'll come to me. Hasn't come to me yet. Check out the next video. Maybe it'll be there. All right. So I practiced doing some division with the radical there. Did you? So let's take a look then. Will you x to the third plus 2x squared minus 5x minus 4. I think you'll like this a lot better. Ooh, I don't actually know if these first two are x-intercepts. Well, the best way to find out is you do the problem and let me know. Okay, so with this f of x is x equals negative root 5 and x-intercept. All right, go find out. Welcome back. What did you find out? Negative root 5, 1, 2, negative 5, negative 4, 1, negative root 5, 2 minus root 5. Distribute that to each of these. So minus root 5 times minus root 5 is plus 5. And minus root 5 times 2 is minus 2 root 5. And I add these, and these cancel, and I just have the minus 2 root 5. And then minus root 5 times positive root 5 is negative 5, times negative 2 is positive 10. 6. Well, so no. Because I didn't get a 0 here, negative root 5 is not an x-intercept on the graph. All right. I'm glad you found that out. What about this one? What if f of x is negative 3x to the third plus 8x squared plus 18x minus 8 is 2 plus 2 root 2 an x-intercept? Mr. Google, you're the devil. Maybe, sometimes. Or just the mischievous math sprite. Okay, so, yeah, I know you're not even gonna try. But really, you should pause it and give it a try. I want to do synthetic division here. Negative 3, 8, 18, negative 8. Put down that negative 3, and I have to distribute that negative 3 to each of these, so I get negative 6 minus 6 root 2. And then I add 8 minus 6 is 2 minus 6 root 2. Look, I have to multiply this stuff by this stuff. 2 plus 2 root 2 times 2 minus 6 root 2. Sure glad we did that when we reviewed radicals. So, FOILing. 4 minus 12 root 2 plus 4 root 2. I did that, and I got to do that one still. Root 2 times root 2 is 2 times negative 12, so negative 24. Okay, these are going to combine to be negative 8 root 2, and these are going to combine to be negative 20. So then I combine these. And remember, we're adding, so we have negative 2 minus 8 root 2. Foiling time! Wow, you know, this math stuff, it's amazing that we learned how to multiply these things earlier, and now that's coming in so handy now when I'm doing this other thing about breaking down this polynomial. So we've got negative 4, and we've got negative 8 root 2, and we have minus 4 root 2, and then when I do this with this, root 2 times root 2 is 2, times negative 16 is negative 32. And so what happens? I've got negative 12 root 2, and I got minus 36. So when I add these, I'm going to have negative 44 minus 12 root 2 as a remainder. So is that a factor? Nope. No, not a factor. Okay, so we are primarily concerned with finding factors, right? Find me those factors. And I know I found a factor when my remainder is 0. Now, sometimes the problems are going to be really gentle, like this one, 2x to the third plus x squared minus 6x minus 3. I don't know if you recall a few minutes ago, we did this with synthetic division. Dude, it's 4 terms, factor by grouping, and say, oh look, I'm going to take out an x squared and be left with 2x plus 1. I'm going to take out a minus 3 and be left with 2x plus 1. And because I have this common factor, I can bring these down and have x squared minus 3. That's factorable as a difference of squares. And so now I have my factored form. Some people don't see that difference of squares. Don't worry if you're one of those people. Remember, we can find x-intercepts by setting the factors equal to 0. And here, when I set this factor equal to 0, I get x squared equals 3, and then x equals, don't forget, you took the square root of both sides, plus or minus root 3. And then from this, I could go backwards and say, oh, that must be these are my factors, right? You can find those x-intercepts and turn those x-intercepts into factors. All right, well, that's quite a lot of stuff there. Yeah, okay, that's our review for today. That's assignment number 47. Next comes complex numbers. I can't wait to see you there. Take care.